And then we know through a drag equation, I was able to calculate myself what the speed would have been when it reached the limousine based upon the atmospheric parameters of the pressure, the temperature, and that's basically the density of the air. So I was able to calculate what the impact speed was. The Zapruder film provides an additional piece of evidence that I would say is definitive.
You're listening to Quorum Radio on WRMI 5850.
Quorum Radio, now on with Dr. Nick Nalli. Nick Nalli is a senior research scientist with a company called IMSG Incorporated. He wrote an academic article titled Gunshot Wound Dynamics Model for John F. Kennedy Assassination. He presented that paper in 2018. It was featured on a Mysteries at the Museum special in 2018, recorded on November 26th, 2018, at the 6th Floor Museum in Dallas, Texas. Dr. Nick Nalli, how are you tonight? Good to have you on Quorum Radio. How's everything going where you are in the Northern Hemisphere?
Hi, Bill. Doing well up here in the Northern Hemisphere. It's summertime, and it's hot and humid out here in the D.C. area. How about you?
It's wintertime south of the equator, where I'm at. And so it's okay. It's I'm hoping to go back to the States soon, in which case I'll have the best of both worlds. I'll go back to summer and leave behind winter. So anyway, why don't we have you on the show? Because this whole matter of the wound that affected our 35th president when he got hit in the head. Some people say from the rear, some will say from the front. I've spoken to Jim Jenkins before, and there's lots of people who said that there was proof that there was a small entrance wound at the front of the head, and other people say that's not true. Maybe that was an exit wound from bullet debris of a bullet that began to fragment and fall and just fall apart as it went through the cranium. And anyway, so that's why I need to speak to somebody who's a research scientist to clear up these doubts. So that's what I call Dr. Nick Nalli. So anyway, Nick, tell us about the paper first of all. What was it? What did it focus? What did it have to do with exactly? And then let's go specific. Again, give us a global perspective on it. A global perspective. So,
I'll give a very quick global perspective as best I can here. So, first of all, my whole interest in the JFK assassination started as a child when I saw the Zapruder film live TV one night with my family, and it was when I was a kid, and apparently that was the Geraldo Rivera showing of it, although at the time I had no idea. And I'm one of 6 boys, so we're kind of a big family, and my oldest brother is also a professor in science, so he sort of had an influence on me, and I heard them all back at me going, oh my, look at that. Yeah, he did go back. He went back. So I heard all that, and I'm seeing what's happening, and I see a lot of what appears to be a very violent thing that's happening, but I have no understanding as to what's going on. So that started my whole interest my entire life through on the JFK assassination. But of course, unlike some buffs, it wasn't like I was always studying it. So I went to college, I went to graduate school, and there were a lot of periods where I wasn't really paying attention. But what happened is within the past 10 to 15 years, my interests got rekindled. And part of that just had to do with the fact that I settled into my job and career. I wasn't, a graduate student anymore, and I have more leisure time, which is what happened. So as I started becoming more interested in the case, I started reading books, and books like Bugliosi and Gene Davison and different books that really kind of got me really interested in the case as an adult or with a different mindset. But as I was getting interested, I kind of was also interested in the science aspects, because that's what I do for a living. And so this Zapruder film had always interested me, and what was observed had interested me. Now, here's an interesting story. Now, back in graduate school, I was taking my classes in what we call classical mechanics and atmospheric dynamics, which are all classical physics. And as I was taking these classes, it dawned on me independently that what happened in the Zapruder film must have been a recoil effect where he goes backwards and to the left. I realized, that's got to be due to a recoil effect. So later on blogs, I came to learn that this physicist Luis Alvarez from the 1970s, who's a Nobel Prize winning physicist, was who I should have known that I didn't, had already come up with this theory of the jet effect. It became what people call the jet effect, although I think he also used the term recoil effect in his paper. So that kind of got me going on the topic. So my initial interest was this jet effect. But in addition, though, there was that those two crucial frames in the Zapruder film, the 312 and the 313 frame, where what we see there is that the two frames between which President Kennedy is shot in the head. The bullet hits, and it's terrible to look at. But you see it, and what's noticed is there's a forward impulse on his head. His head is moved forward by approximately 2 inches. So that the more I pondered that, the more I thought to myself, that is a really big deal, actually. And I don't know if people have really fully understood the full implication of it. Now, again, this was observed. There's nothing. So then it became the sort of thing where I discovered it. No, I did not. I know I didn't discover it. It was discovered back in the 60s, I think, by Professor Feynman, Richard Feynman, who was another Nobel Prize winning physicist. And he, in David Lifton's book, reports this. And I tend on believing that Richard Feynman had noticed it. But then it was Josiah Thomson, who later, with a physics student named Bill Huffman, he was the first to study the frames, and they measured it. They came up with a measurement of about 2 inches, or 5 centimeters in the metric system. And so that data is very valuable data. Now, he wasn't really looking for that, but that's what he found. So having that measurement and then being able to see the frames and to know what the frame rate is and to know a lot of details about what's going on in those frames, I realized that I think that you can actually do a modeling study of this. You can model what's going on. Model just means that you create the equations that determine what you would predict would happen or what should happen given forces. So given the fact that we knew that the mass of the projectile was a certain mass and the speed of the muzzle speed and the speed of impact and the shutter rate of the camera and the mass of the brain and the yield strength of the skull and the drag coefficient of soft tissue and the drag equation for soft tissue, all these things can be put together and you can actually do a very rigorous calculation based upon classical mechanics. So I worked on this. It took me about 2 years of thinking about it, working on it, and I had time when I was on board research ships where I had spare time. I wasn't with my wife, and I was able to think about it, work on it, do coding of it. And so that's what led to finally putting it all together. And I thought to myself, I'm going to submit this as a scientific paper in a peer-reviewed publication because I don't think anybody else has. And so that's what happened. And finally, it did get accepted in this journal called Helion, which is an Elsevier journal. Elsevier is a very reputable scientific publisher located in Europe. So anyway, that's a long-winded answer, but
that's okay. It's a detailed answer. That's good. It's informative. Let me ask you a question. What did you study undergrad and graduate school and postgrad?
So undergrad, I was interested in science education, but with a focus on meteorology and a minor in mathematics. Then when I went to graduate school, for atmospheric and oceanic sciences at the University of Wisconsin-Madison. Got a master's degree and a PhD there with a minor in physics. So interestingly enough, those topics relate very closely to the mechanics of this gunshot wound dynamics. In fact, that's what I call it. I call it dynamics because it's that branch of physics. It really does. All the basic stuff there I had learned about, in classes. It was just a matter of applying it to this unusual case, a gruesome, gory case. A lot of people aren't really too jazzed about studying that type of thing, but really it's basically the same type of physics. It's just a different case and a little bit more complicated because the brain is like a liquid, but it's not. It's what we call a visco-elastic fluid. It's not quite like water. It's got similar properties to water. And I say water because that's what we do. Like what I studied, took a lot of oceanographic classes about the physics of ocean currents and how they get generated, as well as atmospheric currents, atmospheric winds, and both are fluids, right? So the atmosphere is a fluid, and so the brain is like a fluid too. But the only difference is it's a little more complicated because it has elasticity in it. And so, but then I found the equation from Larry Sturtevant, and there was another author as well. The equation that describes the drag forces, and it's a lot like the equation that for the drag forces in the atmosphere and water. So it's very similar, but another term in the equation makes it a little more complicated. But yeah.
Right. Let me ask you a question about just some of the preliminary facts. Do they know exactly how fast the bullet was traveling? How many feet per second?
Yes. Yeah. So they know. We know exactly how fast the bullet left the muzzle. It's called the muzzle velocity. And then we know through a drag equation, I was able to calculate myself what the speed would have been when it reached the limousine based upon the atmospheric parameters of the pressure, the temperature, and that's basically the density of the air. So I was able to calculate what the impact speed was, but that said, so the muzzle speed was approximately 658 meters per second. So let's call it 660 meters per second. And by the way, I have to work in metric units here. I can't give it to you.
No problem. I can figure that out in feet per second, because that 660 is roughly times 3. Then you have 10%, right? So
yeah, I'm pretty sure you can do that.
1960, about 2,100 feet per second, right?
Okay, that sounds about right. So 660 meters per second, but then the impact speed was about 560 meters per second. So it lost about 100 meters per second by the time it reached the limousine at Zapruder frame 312, basically. So lost about 100 meters per second just from moving through the atmosphere, which is really kind of an interesting thing when you think about it.
So it hit. Yeah, I would have thought that would have lost much less. So it hit. Mm-hmm. It hit at 550 meters per second upon impact?
Yeah, about 560 meters per second. Yep.
Okay. All right. That's interesting. So then, and then that divided by 12, because I'm figuring it was roughly 1,787 feet per second. Interesting, which is can do a lot of damage. And so, okay, so give us, so take it away, Nick.
Oh yeah, well, the speeds, are important part of this, because that's the reason why a rifle is so much different from a handgun, because both are bad, right? I mean, they're both bad, but the rifle has a higher energy projectile. It's a higher speed projectile. They're what we often call supersonic, right? So the bullet goes faster than the speed of sound, and so it contains a lot of energy, and it's that energy that creates the really terrible, terrible effect when it interacts with the human body, assuming that the bullet transfers its energy, right? So that's a very important part of all this, right? So this is one of the big questions as to, how could that same rifle cause the JFK neck wound, but then cause the head wound? Now, of course, all this stuff had been talked about, like Dr. John Latimer had discussed these things. So again, there have been others who've studied this stuff and tried to come up with the logical answers, and they came up with the answers, but I can kind of communicate it from a scientist. I'm not a ballistician. I'm an applied scientist who understands that, dynamics very well, basically. So
Sure. Okay.
That I can tell you is, so anyway. Yeah, so it's that high energy aspect, the bullet, that creates the devastating damage, provided that it transfers the energy. And so in the case of the neck wound, what happened is the muscle mass of the neck and the skin, basically, doesn't give you a very lot of, does not give the bullet a lot of resistance. So the bullet kind of passes through it without slowing down very much. And because it doesn't slow down very much, it doesn't transfer very much energy. And because it doesn't transfer very much energy, it doesn't deliver a lot of damage. It just kind of goes through. So number one, it doesn't do much damage to the target. And number two, the target doesn't do much damage to the bullet. So the bullet comes out intact, right? But slowed down. And so I'm getting off on a tangent about the single bullet, but the reason being is it relates.
It's okay.
It's all sort of the same basic stuff, right? But unlike that, when it hit the head, it hits the skull head on at full speed, and the yield strength of the copper and the bullet itself was very close to the yield strength. That was the speed and the yield strength was just right, so that it ruptured the copper nose of the bullet, and that created this sort of, like, it was a hollow point at that point, right? So if you rupture the nose, it becomes like a hollow point, and then it expands, and because it expands, it becomes like a parachute. Because when you think of a parachute, it slows you down.
Right.
It slowed the bullet down, and because the bullet slows down, it transfers its energy, right? So it all goes together. So
Right.
It starts to transfer its momentum, and it transfers its energy. The momentum is what causes the small little forward impulse. The 2-inch forward head snap is created because as it passed through, it transferred its momentum. The energy is what created the devastating wound. So as it transferred its momentum, it transferred its energy, and that created a terrible effect to the target, basically, and to the bullet, right? So the bullet also, by the way, so the other way around, and of course, physics doesn't care, right? We have a moral, we look at it morally that, well, it's terrible that it happened to his head, but his head did devastating damage to the bullet because it's an interaction between the two.
Right. Okay. Sure. So then we're looking at a case of a bullet doing a massive amount of damage. Is it accurate to say? I mean, we're talking about ballistics, and use a pun. Is it let's say proper to say or feasible to say that it did a lot of damage on the way in as well as on the way out?
So it does its damage as it loses speed, and that's what it's really all about. And as it loses its speed, it delivers its energy, and then the energy propagates outward.
Right.
So the energy, unlike momentum, energy doesn't have a direction attached to it. So the energy spreads out, and there are mechanisms behind how that happens that we kind of understand. But in ballistics, they call it the cavitation. The temporary cavitation wound is what they call it. And all that is because it has so much energy that the fluid that's going through, which is the brain, the visco-elastic fluid, doesn't have time to adjust itself. So literally it spreads into two. And then what that causes is a huge pressure gradient, because what's happened is you created a near vacuum. You split the mass in two of the brain, and there's a big vacuum in between, and that's a great pressure gradient. And then not only incredible pressure gradient, but then not only that, but then there's elasticity, which is another force that is a tendency to hold the tissue together. And so that's there as well, and both of those are what create this sort of outward pulse of a pressure wave. So an analogy, I heard Luke Hague use this analogy. It's a very good analogy, would be when you throw a stone into a pond. So you throw the stone into the pond, you have your initial sort of entry area, but then what happens is you get like a splash and you get this wave that spreads out. And it's like that.
Right.
And by the way,
Sure.
think about how the wave spreads out, right? It's quite a bit slower than the initial throw of the stone, right? You might throw the stone in there and you might get a splash very quickly, and then the wave sort of spreads out. It's the same thing here. So the wave that is created from a cavitation wound happens after the bullet is gone. So the bullet had passed through, in the case of JFK, it had already gone through his head, and it was gone, and the wave is still spreading out. Now, this would be something that you would observe if you had a very, very high-speed camera, right? If let's say Zapruder's camera, rather than 20 frames per second, filmed at 1,000 frames per second, you would see all this stuff going on, right? And it would be going on in super slow motion. But because the rate was very slow, you don't see any of this stuff. You just see the before and after.
Let me ask you a question, just a silly question from the peanut gallery, because I mean, I don't know what's possible, what's not possible, but they have been able to break the Zapruder film into, I don't know how many frames, 450 frames or something. How many frames is it?
Well, that's probably about right. I don't know exactly off the top of my head, but that's probably about right.
No problem. Sure. So my question is that, I mean, is any possibility that the bullet can actually be seen just a split second before it hits JFK's head?
Well, it's a good question, because the reason why I say that, kind of with a smile, is because, doing my calculations, as I did all these calculations, one of the things that I determined was it was possible that the bullet, based upon the calculations, which now I'm starting to forget exactly what I did, but it's in the paper, had shown that the bullet, I know what it is. It has to do with the explosion of JFK's head, the development of it, the size of the explosion, the size of the particles that were coming out, gave me an idea as to when the bullet struck. And so the bullet probably struck his head shortly after the shutter closed at Zapruder frame 312. So Zapruder 312, the shutter's open, then it closes and the bullet hits almost immediately when it closed, right? So that means that the bullet might have been in the field of view of the camera. So for example, Zapruder frame 312, the bullet might be in that frame someplace, but the problem though is the frame resolution is just not going to be good enough for you to see it. So you can look there all you want, but you're not going to see it. But it's possible it could be there.
Well, all right, okay. Well, that's out of the way. So anyway, let me let the smart guy continue. All right, just curious about that. So anyway, based on what you saw, what was the damage like? Tell us about the damage based on what you've seen. And this goes on, of course, on the assumption that the Zapruder film wasn't doctored, the body wasn't altered, etc. What's the aftermath? What does it show? Describe the aftermath in JFK's skull and everything, and what it tells us. What does it mean?
Yeah, so there's a
cavitation wound.
Right. There's the basic physics that I was talking about, conservation of momentum, conservation of energy, and that type of thing, which allows you to do the calculations that I talked about. But then there's the details, the actual mechanisms that are going on. So there's the transfer of energy, but what does that do, and how does it go about doing things? So for one thing, is the bullet enters the skull and perforates a hole with it's called a beveling effect or a cratering effect, where the hole is larger on the other side. As it passes through, it breaks more and creates a beveling effect. So that's one thing. Another thing is that the initial pressure caused by that bullet probably causes the skull to bend inward a little bit, because there is a little bit of elasticity, but not a lot. So the skull bones have a little flexibility, but eventually they break, right? So So what happened is that little bit of that pressure point as the bullet pushes through probably causes the skull to kind of bend and then kind of crack. And that creates what they call the radial fracture wounds that apparently are visible on the autopsy X-ray. So there's autopsy X-ray. You can see it. It looks like there are these radiating wounds, but for me, I haven't been trained how to really interpret X-rays, but I can kind of see what looks to be radiating fractures. So that happens. But then the bullet, because of the high speed and the yield strength, is about right at the copper nose ruptures. It becomes a hollow point, and the bullet spreads out in fragments. It becomes like a parachute that slows it down, that allows it to transfer its momentum and energy to the target. Of course, the target has transferred its momentum, its resistance, to the bullet, which is why it fragments and becomes, pulverized, basically. So it's an interaction between these two objects is what all it is. So as it passes through, it creates creates the cavitation, temporary cavitation wound, and that basically spreads the energy out into the rest of the skull. The pressure wave spreads out. It creates an enormous amount of pressure on the skull that surpasses the yield strength of the skull, and that creates other fractures. And these fractures are they're kind of at right angles to the original radial fractures. And so that creates basically what's called, what we would say is like the explosion, what's referred to as like an explosion. Now note that this is not the exit wound. This is just what we call a temporary cavitation wound. It's the wound created by the wake of the projectile. It's not created by the exit wound of the projectile. But then the projectile does eventually exit, and it's gone. But the cavitation injury happens after the projectile is gone, though. So the projectile passes through, and then you have this spreading out of a cavitation pulse and left in the wake of the projectile.
Right.
And that creates a devastating amount of damage.
Go ahead.
So, yeah, I think we've got a little bit of delay here, but so that creates a tremendous amount of damage. In the end, though, these are sort of the mechanisms, the detailed mechanisms that go on. But in the end, fundamentally, it's very simple. You have a projectile that has a certain amount of energy and momentum. And I say a certain amount meaning a lot, because it's a rifle. And as that projectile interacts with its target, it transfers its momentum and energy. And so you might think of when the bullet is fired from the gun, it makes a huge noise, causes a recoil on the rifle, and it's scary because, there's a lot of energy there. All that bullet did was take all that energy and it strikes the target and transfers it to the target. So basically it sets off a firecracker, basically, in the target. And that's what causes that terrible wound.
Sure. Explain what the beveling is. What exactly does beveling mean, practically speaking? What does it mean from the standpoint of what, if one could be looking right now at JFK's skull, what would we see?
So the beveling is simply just the sort of cone that is created in a hard bone, basically, especially like in a skull bone. So it's kind of like what people will say when if a BB gun hits glass, doesn't totally shatter it, you'll see sort of that same beveling effect. And it just gives a forensic
on the other side
investigator and forensic pathologist or whatever evidence as to what direction the bullet was going. So that's what that is. The exact mechanism as to what's going on there exactly, that I'm not quite perfectly clear on. I just know that is what happens. Right. It's an empirically observed phenomenon.
So when you look at, let me ask you a question. I mean, I assume you've looked extensively at the X-rays of President Kennedy's cranium. Can you actually see the beveling? And if so, where is it?
No, not in the X-rays. At least not that I'm aware of. Maybe. All right, let me qualify this. I am unaware of it.
Did they detect beveling?
Maybe there's a pathologist out there who say, "Oh yeah, you can see that there in the X-ray," but I'm unaware of it. I'm not. I can't interpret the X-rays good enough. I haven't been trained in that to tell you that, so I'm not sure. I would say no.
Okay. Okay, but I mean, did they? Of course, there's the X-rays, and then there's the visual observation up close to it. I mean, did the physicians at at Bethesda Naval Hospital perform the autopsy? Did they see beveling? If so, did they mention it in their notes?
Yes, they report that in the autopsy report. Yeah, it's reported there. And they provide sort of the measurement of they give you it's like roughly like an elliptical entry wound, and they give sort of some of the dimensions of the entry, and then they did see a cratered exit, but it was partial. It was like because there was a blowout, so they didn't have the full exit wound, but they had sort of a partial exit wound on the other side as well that showed outward beveling.
Okay. Right. Okay. So based on what you've seen, the movement of President Kennedy's head, what does it tell you?
Yeah.
About
so
what happened in the assassination?
That's the huge $1 million question, and this is something that, again, you can go to Posner's book, you can go to Bugliosi's book, you can go to different books, and they mention this. They mention this forward head snap between Zapruder frame 312 and 313. So it's been observed, but what I feel that wasn't really emphasized was that's the proof that at least the Zapruder film provides an additional piece of evidence that I would say is definitive that the shot is coming from the rear, because it's between those two frames that all the dynamics, all the classical physics that we're talking about here. People want to talk about Newton's laws, and then they don't really fully understand them. Everything happened between those two frames in terms of momentum transfer due to a projectile. Anything that happened after Zapruder frame 313 has nothing to do with the projectile. The projectile is gone and at rest and is not interacting anymore. So it's between those two frames, and what you have to do is if you want to be definitive, you have to do a quantitative calculation of that sort. You have to model it, because otherwise you're just hand waving, which means you're just kind of, it's this, but then you're not really providing a real definitive explanation as what is the implication of that. The point again is the forward head snap between 312 and 313 is definitive that the gunshot wound is occurring from behind. He was shot from behind between those two frames, and that's corroborative with the autopsy evidence. So it's nothing.
Right.
It's not like something that seems odd or at odds with other evidence. It's actually totally corroborative with the other evidence.
Right. Okay. Is there anything in the Zapruder film that suggests, based on the movement of JFK's body and his head, that he was hit from the front? Is there anything in his bodily reactions, movements, etc., that suggests any type of a projectile hitting him from the front of his, at the front of his body, at the front of his head?
Yeah, so that's a good question, and the answer to that is no. There's not. Not in the Zapruder film. There's no indicator whatsoever of a shot from the front. Now, some people would say, "Oh, well, what are you talking about? Back and to the left, back and to the left." The back and to the left motion did not begin until the Zapruder frame 314. Again, the bullet had already done its thing. Whatever happens at Zapruder frame 314 has nothing to do with the bullet anymore. It's something else that's going on. And in this case, it's in the wake of the bullet that other things happen. One of them is the quote-unquote jet effect, right? So that's one of them, or what I call the recoil effect. The other is a neuromuscular reaction. Bottom line is, the back and to the left motion is not due to the bullet. And one other thing, too, is the back and to the left motion involved his entire upper torso. And that means that there would have to be a force on the entire upper torso. But a gunshot wound to the head would be a force on the center of mass of the head. It wouldn't cause the entire torso to go backward like that. There's not enough momentum in the bullet. I don't care what bullet it would have been. You could say, well, it's an M16 or something like that. No, there's still not enough momentum in that bullet to create that effect. There just isn't. I could imagine now, let's take a hypothetical case. Let's say that they had a Civil War cannon on the grassy knoll, and the Civil War cannon has a cannonball that would have enough momentum, right? Okay, but here's the thing. If the Civil War cannon was shot at his head, what that would do is it would, before anything could happen, the energy transfer to his head would just cause him to decapitate. The head wouldn't be attached to the body anymore, and the body would still fall flat. In other words, even a cannon would not cause that reaction. Not even a cannon would do that.
Okay. So then your conclusion is that everything tells you that the shot came from the rear of the president, right?
Yes, that is correct. In the separated film, yep.